Hi, welcome, this is Clemens at Elektor. In this video I will present some small circuits capable of converting a SPI data stream into something compatible with the WS2812B type addressable RGB LEDs without using a microcontroller. Some time ago I made a video about a driver for WS2812B type addressable RGB LEDs without bit banging on an Arduino Nano Every board. This driver used the MCU's custom configurable logic block, CCL, to combine the SPI signals with a PWM signal. An RC network at the output ensured that the pulses were long enough. As the logic used was very simple, only AND and OR gates, I started thinking of a little circuit that would do the same and that then could be used with microcontrollers that do not have configurable logic inside. But before we go any further, let us first review the principle behind the SPI-based driver. For this we must look at the timing requirements of the data protocol of the WS2812B LED. Usually it is said that these LEDs must run at 800 kHz, which is an inconvenient frequency for microcontrollers clocked at 4, 8, 12 or 16 MHz, or any other frequency that is not a power of 2 multiple of 800 kHz. However, when you read the LED's datasheet carefully, you will notice that the timing tolerances are almost 50%, which is rather generous. This means that a data rate of 1 MHz should work too, as it is only 25% faster than 800 kHz, and therefore within the 50% headroom. 1 MHz is a frequency that most SPI peripherals can produce easily, even if they only have a basic clock prescaler. For the WS2812B LED, a logic 0 is transmitted as a pulse of 400 nanoseconds followed by an 800 nanosecond space. A logic 1 is encoded as an 800 nanosecond pulse followed by a 450 nanosecond space. Basically, a logic 1 is the inverse of a logic 0. However, according to the datasheet, all these durations have a tolerance of plus minus 150 nanoseconds. So for logic 0, a pulse of 300 nanoseconds instead of 400, followed by a space of 700 nanoseconds instead of 800 is fine too. And the logic 1 is allowed to be a 700 nanosecond pulse followed by a 300 nanosecond space. With these values the data rate becomes 1 MHz, that's exactly what we were aiming for. When SPI runs at 1 MHz, its SEK clock signal is a square wave with a frequency of 1 MHz. Such a signal consists of 500 nanosecond pulses and 500 nanosecond spaces. To turn it into a WS2812B compatible signal, we must shorten the pulses for logic 0s and make the pulses for logic 1s a bit longer. The data is found in the SPI's MOSI signal. If we extract the rising edges of the SEK signal, then we must turn them into 300 nanosecond pulses when MOSI is low and 700 nanosecond pulses when MOSI is high. It is easy to turn a rising edge into a 300 nanosecond pulse with a differentiator. If we AND the SEK and MOSI signals together, we obtain a signal with 500 nanosecond pulses when MOSI is high. If we now OR the 300 and 500 nanosecond pulses together, we get a signal with different pulse lengths for 0s and 1s. We can make these pulses a bit longer by adding an integrator. This will make the 0 pulses longer too, but we can compensate for that by adjusting the differentiator. And there we are, we now have a signal composed of 300 and 700 nanosecond pulses with a period of 1 microsecond, exactly what we wanted. Such a circuit needs a buffer to drive something. Therefore I added a MOSFET which has a very high input impedance by design and so it won't destroy the signal. Unfortunately, this transistor buffer inverts the signal. To fix this I added a second MOSFET that inverts the signal back to normal. That's almost it. Because SPI is allowed to connect to more than one device, it is a so-called multi-drop bus, I added a third transistor. This one lets you disable the circuit's output so the LEDs won't listen to data that is not intended for them. After trying this circuit on a breadboard, I drew a PCB for it that I ordered at Eisler.net, a low-cost PCB pooling service. A few days later I received the PCBs. Since the circuit is small, I assembled 4 boards to see if spread in component values might have any influence on the way it worked. The circuit turned out to work fine for SPI modes 0, 1 and 3. In mode 2 it still works, but the first pixel is always bright white, while the others won't switch off completely. This is due to the SEK and MOSI signals both being high when idle in this mode. I have tried this circuit with several types of addressable RGB LEDs and found it to work fine in all cases. Note that these LEDs are not all created, or should I say cloned, equal. I have strips labeled WS2812 and WS2812B and unmarked strips with 4-pin and 6-pin devices. It turned out that the unmarked strips were much more tolerant to timing issues than the WS2812 marked strips. I found that the idle time between data bytes is an important parameter. SPI produces a MOSI signal with the bytes separated by a delay needed to load a new data byte. When this delay became too long, my WS2812 marked strips began working erratically, whereas the unmarked strips kept on running. Officially, the data latch time is at least 50 microseconds, but maybe some devices accept a much shorter delay? The SPI data reload delay can become too long due to other processes running in parallel, like timers that interrupt the SPI transfer. It is therefore highly recommended to disable interrupts when data is transmitted to the LEDs. Another important thing is the power supply of the LEDs. This is valid for every design using them. When there are many LEDs, or when the light intensity has to be high, or when there are many white pixels, you must power the LED strip directly from a good 5-volt power supply. Note that the value of the supply voltage of the SPI converter must be the same as that of the LED strip. Even though my circuit works, I found it a bit inelegant, and so I looked for ways to simplify it. Instead of ANDing and ORing the SEK and MOSI signals, you can use MOSI to control the pulse length of SEK. This circuit does that. When MOSI is low, C1 and R1 form a differentiator that shortens the SEK pulses. When MOSI is high, R1 is disconnected and C1 simply passes the SEK pulses to T2. When SEK is high, T2 conducts and C2 is discharged. When SEK goes low, T2 stops conducting and C2 is charged by R2, effectively delaying the falling edge of SEK. Now the SEK pulses are longer. T3 buffers and inverts the signal. Like the first circuit, this one also works in SPI mode 0, 1 and 3. You can decrease the current consumption of this circuit by replacing R3 by a P-type MOSFET with its gate connected to the gate of T3. Now, when the circuit is idle, the output stage is disconnected from the power supply and no current can flow. I even designed a third circuit based on Schmidt-trigger NAND gates. This looks even simpler, but there are, of course, way more transistors involved. Now the pulses for the zeros and the ones are created independently from each other. SEK provides the zeros and MOSI the ones. The gate on the right merges them into one signal. This circuit only works in SPI modes 1 and 2. You could do something similar with monostable multivibrators. And as a fun fact, you can turn the output signal of these circuits back into SPI with a single monostable multivibrator that triggers on the rising edges of the signal. If it produces 500 nanosecond pulses for each rising edge, then the result is the SEK signal. At the falling edge of these pulses, the data is stable, low or high. This is equal to a SPI signal in mode 1. Summarizing, with the circuits presented in this video, you can turn any SPI port capable of running at 1 MHz into a WS2812B type addressable RGB LED port. This allows to simplify the driver software and therefore it leaves more resources available for the rest of the program. Also, it is 25% faster than a standard 800 kHz driver, so you can drive more LEDs in the same time. Okay, that's it. I hope you found it useful or interesting. If you did, please subscribe to our channel and click or tap the bell button. Thank you for watching.